Hello, good morning, good afternoon. So today we are going to see uh, a C++ program to implement hash table data structure. So in this program, we are going to implement the hash table, and we are going to handle the collision using linear and quadratic probing. So in a single hash table, it is not possible to handle both types, that is use both types of collision handling techniques. So what we will do, we will create one hash table, and in that hash table, if there is a collision, we will handle it using linear probing. And in second hash table, if there is a collision, we will handle it by quadratic probing. So after that, we'll do the insertions in both the hash tables. Maybe we will insert the same keys and values in both hash tables, and then we will compare the number of comparisons required to search a set of keys in in both the hash tables, and then we will compare the number of comparisons required in hash table 1 and hash table 2. Hash table 1 where we are handling collision using linear probing, and hash table 2 where we are going to handle the collision using quadratic probing. So the type of hashing we are going to implement in this practical is a closed hashing, where a single bucket or a single location of the hash table is going to store a single key and value pair, right? So let us start. So here you can see is the header files first. So these header files are there, and we have common header files in a C++ program, that is IOStream, and then using namespace std. Along with them, there is a one more header file, and that is C string. Okay, so this C string, or it is like a string.h, which is used for to use the ready-made functions of the string class. So that is string length, string compare, like that. So we are going to use here string compare and string copy. So that is why we have included this header file, hash include C string, along with hash include IOStream, and using namespace std. So after this, let us go ahead and see how we can create a hash table. So this is how we can create a hash table of size 10. So initially we are creating a size variable, that is integer table size equal to 10. And then after that, we are going to create the structure for hash table. So this structure hash table has two types of data members, and that is one is string and second is integer. So string is for key and integer is for value. So why we are taking key as a string and value as an integer? Because key is going to be a client name. Key is going to be client name, and value is a telephone number. So telephone number is an integer value, that is why int val, and client name is a string value, that is why character key. So it's a character array. After that, at the end of structure, you can see here, we are creating hash table 1 and hash table 2. So both are having size 10. So each hash table is going to have 10 buckets ranging from 0 to 9. Okay, so 0 to 9 is the index for each hash table, and both of them are going to have 10 objects, and each object is going to store a single key and value pair, that is client and telephone number. So in hash table 1, HT1, we will handle collision by linear probing, and in HT2, that is hash table 2, we will handle collision by quadratic probing. After that, let us initialize these hash tables. So here we are having a function to initialize the keys and values of hash table. So this function has a name init, and you can see here we have a variable I to access the buckets from 0 to 9. So in for loop, we are going to access the buckets 0 to 9, like I equal to 0 and I less than table size. And then it will be incremented gradually, like I plus plus up to 9. So to copy an empty string as a default value for key or client name, so we are using string copy. So ht1 of I dot key comma empty string that is a dotted collection of dots, and then value will be initialized to 0. So ht1 of I dot value equal to 0. Now similarly for hash table 2, we will access their buckets from 0 to 9 using a for loop, and then we will copy an empty string into the key, and then 0 in value of all 10 objects of hash table 2. So this is how we are going to initialize the keys and values of hash table 1 and hash table 2. So key is a string, so it is initialized by an empty string, and value is a integer, so it will be initialized by 0 as a default value. After this, we will have a hash function. So here what you can see is a hash function. So we are going to use division method, and that division method has a simple hash function that is key mod table size, that gives us a index of the hash table or hash key. But here we have key, which is not a number. So if the key would be a number, we would have directly taken key mod table size, and that would have given us an index of the hash table. But here, as key is a string, so int here we are going to find the addition of ASCII values of all the characters in the string. So how we can do that? So we will access each and every character in the string, like I equal to 0, and while key of I is not equal to /0, we are going to add the ASCII value of each character, like key of I, into a variable that is sum, and at the end of this for loop we will have the addition of ASCII values of all the characters in the key in some variable. Then we will take the sum mod table size, and when you take this sum mod table size, sum is also integer, table size is also integer, so what we get is an index of the hash table, and then from this hash function we will return this index. So this is the hash function we are using, and this function accepts string key and returns an integer index of the hash table, as our hash tables are arrays and these arrays have integer index. After that, this is an insertion function in hash table 1. So you can see this insert hash function for hash table 1. So we are going to write a different insert functions, one insert function for hash table 1 and one for hash table 2. Why separate functions? Because in hash table 1 we are going to handle collision, right? While insertion, if the bucket is already full, so there is a collision. So in hash table 1 we will handle this collision using linear probing, and in hash table 2 we will handle this collision by quadratic probing, right? So that is why we need two separate insertion functions for two hash tables. So here we have this insert ht1 for insertion in hash table 1. It doesn't returns anything, that is why return type is void, and you can see it accepts two parameters. First is string and second is integer. So client name and telephone number are the parameters for this function, and it has variables, local variables int I, id, and index. So here we are using index to catch the index returned by hash function here by processing client. So the client name received in a parameter, we will pass that client name string to the hash function, and it will return index, right? Index of the hash table. And then we will use that index to check whether on that location of hash table there is a collision or not. So how we will check that? So if that location of hash table for which the index is generated has an empty string, so there is no collision, right? So we will check whether this empty string is matching with the location generated by hash function. So that is ht1 of index.key. So if that is matching, there is an empty bucket on that location, then we will simply copy the string, and that is client name and telephone number. So as client name is a string, so we cannot copy it by assignment operator. We need to use strcpy. So the client name is copied on the index, that is ht1 of index.key. and then telephone number will be assigned to ht1 of index.val. So this is the case when there is no collision. If there is a collision, that is, the string compare function returns a value which is not equal to 0. So until this collision is there, what we do, we will find an alternate empty location by adding 1 into the current index every time. So initially we will add 1, and then we'll take 1 into the index. Then we will take its mod with table size, and we'll again check whether that location of hash table is empty, right? If that is also not empty, then add 2 into the index, that is the index which is already having 1 added, again add 1, so that is adding 2, then adding 3, and so on until we do not get an empty location. So once we get an empty location, this condition will become false, that is this string compare will return 0. So as soon as we get an empty location, copy the client name and telephone number on that location of hash table. So this is how we will insert in hash table 1. And if there is a collision for which the index is generated, then we will handle that collision by linear probing. After that, in hash table 2. Now in hash table 2, we have a function insert in hash table 2, that is ht2. Now you can see return type of the function is void, as this function doesn't returns anything. So return type is void, and it accepts 2 parameters again, same as the above function, client name, which is a string, and telephone number, which is a integer value. After that, we have this local variables, integer I and index, and we are passing client name to the hash function. Hash function will generate an index of the hash table by processing key client name, and then we will catch that index into the index variable. Now on this index, we will check if there is a collision. So if the string compare returns 0, that means on this index there is an empty key. So there is an empty bucket. So string compare returns 0, that means there is no collision. If there is no collision, what we will do? We will straightforward copy the string client name and telephone number on that location. But else, that is otherwise, if there is a collision, so in hash table 2, we are going to handle this collision by quadratic probing. So we will initialize I equal to 1, and we will copy this current index into ID, and on that current index, the string compare returns not equal to 0. That means that bucket is already full. There is no empty string. So what we will do? We will add square of I square into index, and then we will take its mod with table size. And then we will increment I by 1. So initially I is 1, now it becomes 2. Now when I was 1, we have added its square with index, and that is a mod with table size, and what is the result is catched in ID. So on that location, we will check whether we have an empty key or empty bucket. If that location is that location is also full, that is string compare returns not equal to 0. So then what we will do? We will check, we will add square of 2 into the index, and then we will take mod with table size, and on that location we will check whether that location is empty or not. So this process will be continued like index plus 3 square, index plus 4 square, and so on until we do not get an empty location. So as soon as we get an empty location, this condition will become false. That is, string compare will return equal to 0. And on that location, we will copy what? Client name and telephone number. So this is how insertion is happening in hash table 2. And if there is a collision, we are handling it by quadratic probing. Okay, so this is it. Now this is a display function to display hash table 1 and 2. So you can see here we have declared I, as we are going to copy the index of the hash table, that is for 0 to 9. Okay, and we are going to display bucket, that is index, and then key and value pair on that in that bucket. So this is how we are going to display it in a single row, that is bucket number, key and value. Same for hash table 2. Okay, so this is a hash, this is a display function for hash tables 1 and 2. Now after display, we are going to search the keys. So we know that in hash table 1, we are going to search the keys. And if we do not find a key on current location given by hash function, so we have to check it on the alternate empty locations. But that is depend with while insertion, which probing we have done. So if during insertion we have used linear probing, for searching also we will use linear probing. So for hash table 1, we will use linear probing, and for hash table 2, we will use quadratic probing. So you can see here for searching, we are passing client name, and this function will display the telephone number of the client, okay, in written, as well as it will also display how many comparisons required to search that client name. If this client name is present on the actual location given by hash function, so the number of comparisons required are only one, that is time complexity to search is big O of 1. But if we have placed that client name by probing, so it may take the comparisons which are more than one, right? So you can see here this search function in hash table 1 accepts client name as a parameter, and its return type is void, as it doesn't returns any value. So you can see here in index, we are accepting the index generated for client name. So hash function processes client name and then it returns the index. Now we have declared count equal to 1 for to count the number of comparisons, and then ID is catching the index returned by hash function. Now on this index, we will check whether the client name is present. So client name is a string, and key present in hash table is also a string. So we are comparing two strings. So if these are matching, that is equal to string compare equal to 0, that means we found what we are searching, right? So we will display the key value and number of comparisons, that is 1. So if there is no collision, we directly found the key. So number of comparisons are going to be 1. That is why I declared count is initially 1, right? After this, if there is a collision, that means we do not find the key on the location given by hash function. So that means the key is not placed on its actual location, maybe because that bucket was already full. So we would have find an alternate location by probing, and then we would have placed that key and value. So let us check by probing. So here in hash table 1, we will do this probing by linear probing. Sequentially, we will check. So I is equal to 1. And while string compare does not return 0, we will continue this. And every time we will add 1 into the index, and then we'll take its mod with table size. So initially I is 1, then 2, then 3, and so on. So this is linear probing. And along with that, we will increment number of comparisons count, that how many times we are doing the comparison, right? So ultimately, when we find the key, we will display the key, that is client name, value, that is telephone number, and the number of comparisons required to find that key. So this is how searching happens in hash table 1. Now in hash table 2, the same function is there, just that if there is a collision, we will handle it by quadratic probing. So you can see here, this is the function for search in hash table 2. So the return type is void, and parameter is client name, which is string. So we will pass this client name to hash function, and we get an index. Count is initially 1. Index is stored in ID. So on that index, we will check whether the client name is matching. If it is matching, display key, value, and comparison as 1. If it is not matching on that location, then we are doing what? Index plus I square mod table size, and then storing it into ID. So index plus 1 square mod table size, then index plus 2 square, index plus 3 square. It will continue. So we are incrementing I, we are counting the comparisons into the count. And this process will continue until we find a key. And once we find a key, string compare returns 0. And then we will display that key, that is client name, telephone number, and the number of comparisons required. So here we are using quadratic probing to search a key in hash table 2. Now this is the main function. In main function, you can see this is actually a title for the program, C++ program to implement hash table data structure. And there is an init function to initialize the hash table initially, which we have written over there, which actually initializes a string to an empty string and value to 0, right? That is telephone number to 0. Now this is how we are calling insert for hash table 1. So Amol, Amit, Ajay, Sanjay, Sanika, these are the keys and along with their telephone numbers. So keys and value pairs. Now this is how we are inserting in hash table 2. Again, Amol, Amit, Ajay, Sanjay, Sanika, and their values as telephone numbers or mobile numbers. Now after inserting in hash table 1 and 2, we are going to display the hash tables using display function. And then we are going to search initially in hash table 1 and then in hash table. So these are the search for Sita, Sanika, and Babita. And for each client, we will display client name, telephone number, and the number of comparisons required to search that client name and his or her telephone number. Now, similarly for hash table 2 also, we are searching, right? So Sita, Sanika, and Babita, right? So let us see what is the output. At the end, we are returning 0 from the main function. So this is how we get an output. So hash table 1, where we have inserted these records like Amol, Amit, Ajay, Sanika, Geeta, Babita, right? And there are 9 buckets, you can see 0 to 9, right? So each bucket is storing a key and value. Key is a client name and value is a contact number or telephone number, right? Mobile number. Similarly for hash table 2, and then you can see in hash table 1, when we have searched for Sita, so we find Sita along with, so we displayed her telephone number, and the number of comparisons required to search Sita is 1. So why this is 1? Comparisons are 1. Why? Because we found Sita on the same location where Sita should be present. That is an actual location generated by hash function, right? So when we pass Sita as a client name to the hash function, the hash key will be what? An index, which is an actual location for Sita, right? Now, on the other hand, you can see Sanika. For Sanika, we need 2 comparisons. Why? Because Sanika is not present on her actual location. So it is present on one location ahead, one location away from her actual location. That is why 2 comparisons are required, because in hash table 1, we are using linear probing to search, right? Now, Babita is requiring 4 comparisons. Why 4? Because Babita is 3 locations away from her actual location, right? So 1 comparison for her actual location and 3 more comparisons for next 3 locations. Okay, so that is why 4 comparisons. So if the current actual location of Babita is maybe location number 6, so Babita is not on location 6, she is on location number 9, right? So 6 is 1 comparison for location 6, location 7 2, location 8 3, and location 9 4, right? So this is because linear probing. Now in hash table 2, we are using quadratic probing for insertion and searching. So you can see for Sita, 1 comparison because she is present on the actual location, okay, given by hash key. And Sanika, for Sanika, we need 2 comparisons. And for Babita, you can see 46,344 comparisons are necessary. So why these many comparisons are necessary? Because in quadratic probing, we may not getting the location of Babita easily. So that is why these many comparisons are required to reach, because in quadratic probing, we are adding squares of 1, 2, 3, and so on into the index. So maybe these number of comparisons are required to reach the location of Babita. If we go sequentially, if we search sequentially like we do in linear probing in hash table 1, so Babita is just 3 locations away from her actual location given by hash function, right? The address given by hash function. So that is why only 4 comparisons required in linear probing. But quadratic probing do not search sequentially. It uses I square. So initially it is square of 1 added into index, then square of 2 is 4, square of 3 is 9, square of 4 is 16. So it is maybe giving the locations which are not for the location of Babita, right? So this is how high number of locations are required, large number of comparisons are required to search the records which are placed or which are inserted after collision. So I think for linear probing, it's good if the size of the hash table is less, and quadratic probing is good if the size of the hash table is large. Okay. So for a small size hash table, I think linear probing is good to for insertion and searching. While in case of if the hash table is large, maybe quadratic probing will give you a better result. So this is all about hash table implementation and its operations, that is creation of hash table, insertion and searching. So I hope you have understood this implementation of hash table along with its output. So this is what the title we are looking at. You can see it that today we have seen this program, that is a program to implement hash table data structure, and collision is handled using linear and quadratic probing. Along with that, we have compared the number of comparisons required for searching a set of keys. Okay, so that is it. So thank you. I hope you have enjoyed this session.
Hello, apa? Tadi, tadi, it has to be